So last class we had discussed a little bit about Earth's magnetic field. Then we started talking about what happens to a charge when it moves in a magnetic field. Okay, the force it experiences and the effect of that force. We just started discussing the effect of that force. So the magnetic force acting on a charge F is equal to Q V cross B only acts in a direction perpendicular to the velocity. So that's the most important point. And a force acting perpendicular to velocity makes the object take a turn. Okay, it cannot change the speed of the object. It cannot increase its speed. It cannot decrease also, but it will make it deviate. Okay. So we discussed the magnitude of the force. Then we were discussing the different cases. When velocity is parallel to magnetic field or exactly opposite to it, the cross product becomes zero, the force becomes zero. And when velocity is perpendicular to the magnetic field, if the magnetic field is uniform, the particle moves in a circle like this. Okay. So we'll discuss this case elaborately and then we'll move on to the next case. Solve one question first. An alpha particle and a proton. Okay. Let's say their speeds are in the ratio 2:1. So alpha particle speed to proton speed, the ratio is 2:1. And they enter a uniform magnetic field. They both enter into the same magnetic field, okay, with speeds in this ratio. Okay. So derive or calculate the ratio of first case, radius, and then time period of the uniform circular motion that they execute. Okay, try this all of you. They enter into the same magnetic field. So magnetic field is same in both cases, and they enter into it perpendicular to the magnetic field. And we know when a charge moves in a magnetic field perpendicular to it, it executes uniform circular motion. So derive the ratio of radius of that circular path and the time period of that circular motion. Can one of you quickly tell me what an alpha particle is?
So the helium nucleus.
Helium nucleus. What all will be there in it?
There will be neutrons and protons only.
How many?
Like two, sir.
2 protons, 2 neutrons will be there. So alpha particle is a combination of 2 protons and 2 neutrons. Okay, proton is simply a proton, a single proton. Okay, try this all of you. I'll give you 1 minute. Any answer, anyone? I got one answer for ratio of radius as 1:2. We'll see. Another answer as 1:1. Okay. Rishi, can you tell the formula for radius of the circular path executed by a charge?
Sir, I'm not sure.
Okay, we had derived that in the last class. See, if you are not sure also, it's quite possible that you don't remember all the formulas that you come across in your syllabus. You should know how to derive it then and there. Okay. The force that a charge experiences when it moves perpendicular to a uniform magnetic field is QVB. You equate that to centripetal force, the formula for centripetal force mv square by r. From there, you get an expression for the radius. Okay, so that's why practicing derivations is most important. So if you equate QVB to mv square by r, you get r as mv by qb. That is the radius of the circle in which the charge would move. Okay, we have to make use of that here. So radius r is equal to mv by qb. And you are asked to derive the ratio. So radius in which the alpha particle moves to radius in which the proton moves, that ratio would be mass of alpha particle, speed of alpha particle divided by charge of alpha particle, magnetic field, to mass of proton, speed of proton divided by charge of proton and magnetic field. Okay, that's how you take ratio. Okay. Isha, can you tell me the ratio of mass of an alpha particle to the mass of a proton? No response. Anyone? What is the ratio of mass of alpha particle to that of a proton?
4:1.
4:1. See, an alpha particle has two protons and two neutrons inside it. And proton and neutron, their mass is almost the same. So two protons, two neutrons, okay, two protons plus two neutrons, their mass, okay, so mass of two protons and two neutrons is approximately equal to the mass of, or 4 times the mass of a proton. Okay, because two neutrons have almost the same mass as two protons. So totally it's like 4 protons. And denominator is proton. So mass of alpha particle to mass of proton will be 4:1. Okay. And in the question, it is given to you that their speeds are in the ratio 2:1. You have to make use of that. Alpha particle to proton, the speed ratio is 2:1. Magnetic field is the same that was given in the problem. Then the charge. Alpha particle has two protons, two neutrons. Neutrons don't have charge, but protons have charge. So the charge of an alpha particle will be 2 times the charge of a proton because it has two protons in it. Okay, so I should write it as 2e. The magnitude of charge on a proton is same as the magnitude of charge on an electron. We denote it by the symbol E. Okay, and the charge of a proton is 1e. Right. E can be cancelled. This 2 can be cancelled. The answer for ratio of radius will be 4:1. But surprisingly, I didn't get that answer from any of you.
I forgot to
Anyway.
consider the mass ratio.
You forgot to?
Consider the mass ratio. I took the mass ratio.
Okay. Fine. That's what you need to be careful step by step. So that is, those are, okay, that is the ratio of radii in which they would execute circular motion. The next part of the question is time period. Time period with which the alpha particle would revolve to time period with which the proton would revolve. And do any of you remember the formula for time period?
2 pi m by qb.
2 pi m by qb, correct. So it becomes 2 pi mass of alpha particle by charge of alpha particle, magnetic field, is to 2 pi mass of proton by charge of proton, magnetic field. Okay, mass of alpha particle to mass of proton, the ratio is 4:1. Charge of alpha particle to charge of proton, the ratio is 2:1. So 4/2 is 2. The effective ratio becomes 2:1. And we had discussed this point in the last class also. The time period of revolution of the charged particle in the magnetic field does not depend on its speed. Okay, that is why in the second part of the question, the speed ratio did not matter. Okay, when speed increases, the radius also increases. So if speed is more, it will have to cover more distance, but it takes the same time. Okay. Now see, this is one way of asking. Such questions are very common. Okay. Another way of asking question. An alpha particle, okay, observe the question carefully, and a proton accelerated by the same potential. Enter perpendicular to a uniform magnetic field. Okay, same. The question is same again. Calculate the ratio of radii of the circular paths they would follow. And second part, time period. Okay, time period, you can easily do it. But can one of you tell me how to approach such questions? It is given that they are accelerated by the same potential. We know their mass ratio, we know their charge ratio, and you need to find out the ratio of radii of the circular paths that they execute. We know ratio of radii must be calculated like this: mv by qb. Mass ratio is known, charge ratio is known, magnetic field is the same. We need the ratio of their speeds. How to get that?
Sir, since they're like accelerated by the same potential, it'll be same, right? So you can just cancel it out and calculate it from there.
How do you say that if they are accelerated by the same potential, the speed will be same?
Oh, yeah.
See, we can accelerate charges by making them go through a potential difference. Fine. We have to somehow link that to the speed of the charge. So can any of you come up with an idea how to do that? Okay, fine. Can one of you define potential? Basic definition or formula of potential.
Change in potential equals kinetic energy acquired.
Change in potential?
Equals kinetic energy acquired.
No, it's not change in potential. Change in potential energy will be equal to change in kinetic energy, or negative of change in kinetic energy. But I'm asking, but in the question, they said the charges are accelerated by the same potential. Okay. So what is the definition of potential? Okay. V is equal to U divided by Q. Potential at any position is the potential energy per unit charge placed at that position, which means the potential energy of a charge can be calculated this way: charge multiplied with the potential. Okay. And if the charge goes through a potential difference, say delta V, then it will undergo a, there will be a change in its potential energy. Like if a charge goes through a potential difference, it will go through a difference in potential energy as well. So you can say delta U is equal to Q, the charge, multiplied with the potential difference. So the change in potential energy will be charge into change in potential. That's the idea. And this will be equal to change in kinetic energy. Actually, we are only talking about the difference. When potential energy increases, kinetic energy has to decrease. They'll be negatives of each other, but magnitude wise, they'll be equal. Okay. And here in the question, they said that alpha particle and proton are accelerated by equal potentials. When they use a statement like that, it means they are starting from rest. Okay. And if a charge is starting from rest, the change in its kinetic energy will be half mv square minus u square. U square becomes 0. So that will be half mv square. The final kinetic energy itself will be the change in kinetic energy. Okay. Therefore, when a charge q goes through a potential difference delta v, it gets a kinetic energy of q delta v. So you can equate q delta v to half mv square. That way we can get the ratio of their speeds. So let us do that first. It is given to you in the question that alpha particle and proton are accelerated by the same potential. So first for the alpha particle, charge of alpha particle is 2e, and let's say the potential difference that it goes through is delta v, delta capital V. Then that should be equal to the kinetic energy that it gains, mass of alpha particle multiplied with speed of alpha particle squared. Next, for the proton, if you write that, charge of a proton is E, potential difference, it goes through the same potential difference. So the energy it gains is E into delta V. Should be equal to, it shows up as kinetic energy, so half mass of proton, speed of proton squared. Divide these two, you will get the ratio of speed of alpha particle to speed of proton. And once you get that ratio, you can substitute that in the ratio of radius. Okay, see, this is the only unknown. No, speed of alpha to speed of proton was not known to us. That you substitute there, you can solve the problem. Okay, you can complete this later, but remember the idea. Many times, not just in this problem, in electrostatics, they could give you questions like this. In what is that? Atoms, you can have questions like this. Okay, because I don't know if any of you have studied the chapter atoms yet, but in atoms there is a concept like Rutherford alpha ray scattering experiment. An alpha particle is sent at a high speed towards a nucleus. Okay, so there also they use terms like this: alpha particle accelerated by a certain potential is sent towards a nucleus. What will happen to it? Such cases. Okay, so remember, when a charge is accelerated by some potential, it gets an energy of q delta v. Q is the charge, delta v is the potential difference by which it has been accelerated. Okay, and that q delta v can be equated to its change in kinetic energy, and we are assuming it started from rest, so its final kinetic energy itself will be q delta v. From that you can get a rough idea of its speed and all. Fine. And a slightly quicker way of solving this problem, see, if you observe the radius formula, it is mv by qb. What is mv for any particle or object? Momentum. Okay, so it's momentum of the alpha particle to momentum of the proton. And q delta v gives you kinetic energy. And we know kinetic energy of any object is p square by 2m. That's the basic relation between kinetic energy and momentum. So instead of equating it to kinetic energy, getting the ratio of speed, and then substituting the ratio of speed, directly write q delta v is p square by 2m. You can get the ratio of their momentum. Okay, with that, like, you will be omitting one step. You can solve the problem a little quicker if you take the momentum ratio direct. Okay. Fine. So today I'll send you a worksheet with more questions based on this. You should get used to this. Charge being accelerated by a potential difference is very common. Yeah. Fine. Let's go back to this case where a charge moves in a circle inside a uniform magnetic field. Okay. Consider a situation like this. Suppose there's a boundary here. Okay, it's not a physical boundary, it's just an imaginary line. And on the right side of that line, there is a uniform magnetic field directed into the plane of the screen. Let's call it B. Assume a charged particle. Take it as plus q having a mass m moving with a speed v or velocity v in this direction enters into that magnetic field. So till it reaches that boundary, nothing will happen to it, because on the left side of that boundary, there is no magnetic field. Okay. So it will continue moving with that velocity. We are not considering gravity or any other forces. Okay. For now, we are only studying what happens to a charge due to a magnetic field. So one of you tell me, what will happen to this charge after it enters into the magnetic field? Think carefully. You should be able to describe the complete picture. So your answer will be based on the force that the charge experiences. The force it experiences is QV cross B. So I want you all to think of the direction in which this force would act, how much force would act, what would happen to the charge due to this force, okay, and how it is going to move as time passes. So raise hand if any of you can describe the motion of this object. Okay, yes, just a moment. Let others also think. After that, you can tell. Okay, yeah, yes, you can answer. We know that till it enters into the magnetic field, it will move in the same manner. It won't undergo any disturbance. So the charge is going to enter the magnetic field with the same velocity v in this direction. The moment it enters, it will be like this. Yes, what will happen after that? What is the direction of force acting on the charge?
Sir, its velocity is towards right and the magnetic field is inside our screen. So the force acting will be upwards.
Okay. See, V is to the right and B is inwards. So the direction of V cross B is upward in this case. And the charge is positive. That factor also should be considered. The charge is positive. So the direction of force acting on it will be in the upward direction. Okay. Rishi, you said it moves in a semicircular path. That is also correct. Okay. So it will experience a force this way. And the force acts perpendicular to velocity. So it will deviate in the direction of the force. Correct. Yes, go ahead. Force acts this way. So what happens to the particle due to this force? How is it going to end up moving?
Sir, here the magnetic field, like the force due to magnetic field, it will change its radial acceleration.
It will produce radial acceleration. Yes.
And then it will move in a semicircular path.
Okay. See, the force deviates the charge away from the direction in which it is moving. So next moment it will turn this way. Okay. After that, it will turn this way, and so on. It will end up moving in a curved path. It will try to move along a circular path. But if you imagine how it moves, after completing the semicircle, the charge reaches here. Okay. See, as long as it is inside the magnetic field, it will experience that force QV cross B, and at any instant, the force will be perpendicular to the velocity. So it will keep taking that turn. It will keep turning. So it will try to execute circular motion as long as it is inside the magnetic field. But the moment it reaches that other point, let's name them as A and B. A is the point where it enters into the magnetic field. B is the point where it is about to leave the magnetic field. At that moment, at that position, its velocity is to the left. Okay. And with that velocity, it is going to cross that boundary. Once it crosses that boundary, there is no magnetic field. Okay. So the force will stop acting on it. And when no force acts on an object, what will happen? It will travel with uniform velocity. So it goes like this. Right. Correct. So it is true that it executes it completes a semicircle and then leaves the magnetic field. In fact, this is an idea used by scientists to deviate charged particles. Okay, in any experiment, if they want to deflect charged particles, this is what they do. They switch on a magnetic field, and that magnetic field makes the charges take turn. Okay, so they can deviate charged particles as required. Okay, fine. Now in this case, will the radius still be mv by qb, or will it be something else? Radius of that semicircle, will it be mv by qb itself or not? Shashank, what do you think? Will the radius be the same mv by qb, or will it be something else?
I'm not sure.
Okay, how do we calculate the radius of any curved path generally? It all depends. Yeah, go ahead. Okay, anyone? How do we calculate the radius of a curved path in which an object moves? Like based on its speed and all. Okay, let me explain a general idea to all of you. Suppose there's a particle moving with some speed, okay, or velocity this way. Now, if you want to deviate it from its path, you need to apply a force perpendicular to its velocity. So that radial force is necessary, radial acceleration is necessary to make an object take a turn. Fine. Now, if you apply only a small amount of force, from common everyday experience, we can tell if the force is very small, you can't deviate it much in that direction. So what happens? It will follow a path somewhat like this. It'll have a large radius of curvature. It'll deviate very slowly. But if the force is very strong, you can make it deviate quickly. Fine. So the radius of curvature of the path depends on how much force acts in the radial direction. Okay. It depends on its radial acceleration actually, which in turn depends on the radial force, which is what we call as centripetal force. So just by knowing the magnitude of that force, you can tell what is the radius in which an object moves, not just in case of charge moving in a magnetic field. This is generally true for any curved path. Okay. At any instant, if you want to find out the radius of curvature, you need to know how much force is acting perpendicular to velocity. And you can equate that force to mv square by r. Okay. Fr is radial force. Equate it to mv square by r. From there, you will get the radius of curvature at that moment. Okay. In fact, I don't know how many of you have done this, but even in 11th class, like you would have come across cases of two-dimensional projectile motion. In projectile motion also, it's not a circle. The path followed by a projectile under gravity is not a circle, it's a parabola, we know. But a parabola is also a curve. At different points, it will have different radius of curvature. Okay. So there also they can ask you to calculate the radius of curvature. Suppose they ask you a question like calculate radius of curvature of the parabola at h max. Okay. Then what you do, imagine the particle at h max first. To calculate radius of curvature, what do you need to know? You need to know mv square by radial force. Fine. Now assume the mass is m. In fact, you don't need to know the mass. It only depends on acceleration and speed. But let's say the particle's mass is m. At h max, it will have a velocity of u cos theta. That horizontal component will be there. Okay. And the force acting on the particle when it is at maximum height or any time during flight is gravity. Gravity acts this way, vertically downwards always, mg. And when the particle is at h max, exactly at that position, it so happens that gravity is directly perpendicular to the velocity. So this itself becomes the radial force. That's all. Then you can tell the radius of curvature as m v square, that is u cos theta whole square, divided by the radial force mg. That's all. That is the radius of curvature of that parabola at h max. You can calculate radius of curvature at any other point also. For example, at this position, you first have to find the speed at that position. Equations of kinematics can give you the speed. Then gravity acts this way. Resolve it into components. Okay. like based on that height, it's a lengthy question actually. You can find out at what angle the particle is moving. If you know that angle, you can take the component of mg in a direction perpendicular to its velocity. Then that becomes a radial force. Once you know the radial force, just use this formula. You can tell the radius of curvature at that instant also. Okay, so this is a general idea. The radius of curvature of an object, whether it's a charge or a ball projected or a car moving on a road, whatever it is, depends on the force acting perpendicular to its velocity, depends on the radial force. And this is the formula to calculate the radius of curvature. So come back to this problem. Once it enters into the magnetic field, see the velocity is to the right, it's in the x direction. Magnetic field is in the z direction. Okay, so they are perpendicular. If magnetic field is perpendicular to velocity, the force experienced by the particle becomes qvb, and that force will automatically be perpendicular to velocity. Okay, it's a law of nature that magnetic force is always perpendicular to velocity. So you can directly equate this to mv square by r, and r will still be equal to mv by qb. So whether it completes the circle or executes only a part of the circle, the radius is going to be mv by qb if conditions: the field is uniform and the velocity is perpendicular to magnetic field. Okay, right. So the radius of curvature of this semicircle will be mv by qb. So this is the radius. So you can even tell from where the particle is going to come out of the magnetic field. Questions like this have already been asked in many exams. They tell you that the particle enters the magnetic field at the origin. Okay, so it enters at the origin. They ask you where it leaves from. Okay, so you need to know the radius in which it is going to take that turn. Fine. So in this case, what happened is the charge entered perpendicular to the boundary, and so it so happens that it completes a semicircle before leaving the magnetic field. Okay, let's consider another case. Think about this carefully and solve, all of you. Again, consider a boundary. To the right of the boundary, there is a uniform magnetic field. It is important to note that it's a uniform field, because if field is not uniform, the force QVB will not have the same magnitude everywhere. Okay, if B doesn't have the same magnitude everywhere, QVB won't be same everywhere. That means the centripetal force is not same everywhere, then the radius of curvature won't be same everywhere. It won't be a circle. Okay, we had discussed this in last class also. So consider a magnetic field like this to the right of the boundary. A charge enters into this magnetic field this way. The speed with which it enters is v, the charge is plus q, its mass is m, and it enters making an angle alpha with the x-axis. Okay, so this is the situation. I want you all to imagine first how, or the path followed by the particle. Next, you need to find out time spent inside the magnetic field. If you think it will be in the magnetic field forever, then the answer is infinite to the second part. Then total angular deviation of the particle. Okay, like you have to imagine what happens to it later up to infinite time, and up to infinite time you should find out how much it rotates. Okay, I got one answer as path followed will be parabolic. Yash, why do you think the path will be a parabola?
Sir, can you just show me that first question, sir?
The previous one.
Yes, sir.
Yeah, okay.
Sir, here it was a semicircular path, right?
In this case, it was a semicircle.
And at the center was at the starting of the field. And it's like this.
The center of that semicircle falls on that boundary. Yes.
Now, in the second case, if you visualize, the center will be outside of the field, right?
Okay. So, listen, all of you, what he is effectively saying, trying to say is that this time the boundary is somewhere here. Okay. And we are looking at the charge from the moment it enters into the magnetic field here. So he's saying the center will be outside the boundary this time. When you're talking about a center, whose center is it? Yes. It's the center of what?
The curve, like the radius of curvature of the path which that charge will follow.
But when you say center, you are indirectly meaning it's a circle, isn't it? Circle or semicircle, an arc. Arc can have a
Yes, sir.
center. No other path can have a center. There's nothing like center for a parabola. There is a focus for a parabola, but not a center. So yeah, this time the center, as you said, that yellow point will lie outside. But how did you conclude that the path is a parabola?
So like it looks like a parabola. So
So you are saying, I mean, any curve like this, you'll call it a parabola.
no, sir.
Any arc you'll call a parabola. Arc is an arc. How can you call it a parabola? You're stealing its identity. Okay. Your visualization was correct only. I got one more answer as helical path. Seshank, can you tell why it will be a helix?
Since it enters at an angle, both components of velocity will be active. So one component will make it move in a straight path, straight line, and
Wait. Okay, I understand on what basis you are saying all that. Okay, you may have studied what happens when velocity is not perpendicular to magnetic field. So, but listen, here the angle alpha is the angle made by velocity with the x-axis, not with the magnetic field. Seshank, you tell me which way is the magnetic field in this problem?
into the speed.
So that is like z direction, right?
Oh,
Velocity makes an angle alpha with x-axis, but it's in which plane? Velocity is in which plane?
XY.
XY plane. Any vector which is in the XY plane, what angle does it make with the z-axis?
90.
90. Okay. The velocity in this case is still perpendicular to the magnetic field. It is not making some other angle. Okay, is that clear? Yeah. And see, generally, when velocity of a charge is perpendicular to a magnetic field, it experiences that force QEB in the centripetal direction. Okay, that is the radial direction, and it will try to move along the circle as long as it is inside the magnetic field. So here, the particle tries to execute circular motion itself. Okay, and the way Yash visualized it was correct, but the answer was wrong. So listen, it is effectively what we are now looking at in the second problem is like a part of the first problem. It's like the charge is now, according to the question, the charge is now somewhere here when it enters into the magnetic field, moving this way. And the boundary is here. But as long as it is inside that magnetic field, it's on the right side of the boundary, it will try to execute a circle. So it will move along this curved path, along this circular path. Okay, I can't call it a complete circle, it's an arc. It moves along this arc. And the moment it reaches this point, it comes out of the magnetic field. So it goes off like that. So you won't call it a parabola, it's an arc, which is part of a circle itself. The center will still be here only. Okay, so what Yash told is correct. The boundary will, the center will be outside the boundary now. The path is still circular, or you can call it an arc. So in this case, let's visualize. I'll erase the questions, or I'll paste the questions on the right side. Just a moment. Okay. So here, if you imagine what happens to the particle, the moment it enters into the magnetic field, it starts experiences of force, and we know that the force is perpendicular to velocity. So force acts like this along some direction this way. Continues moving. At the next instant, the velocity changes its direction. Due to that force, the velocity changes direction. Then if velocity rotates, force must continue to be perpendicular to velocity. So force vector also rotates, becomes like this. Extend it. You see these lines meeting somewhere here. So that becomes the center of the circle in which the charge tries to move. Okay, so that is that center now. And it tries to move along that path, but it won't be able to complete the circle. It follows a curved path like this. Okay, as if that yellow dot is its center. Follows a curved path somewhat like this. And the moment it reaches this point, okay, that's the boundary of the magnetic field, right? At that point, its velocity will be in this direction. And with that velocity, it will come out of the magnetic field. Once it is out of the magnetic field, there won't be any magnetic force acting on it any further. So it will go off like that. So if you visualize the complete picture, just a moment. The situation is actually like this. The charge came this way, takes a turn, and goes off like this. That is what is going to happen. And the turn that it takes is an arc, which is a part of a circle whose center is that yellow dot. The radius of curvature is still mv by qv. Okay. Had you allowed it to complete the circle, it would have executed a circle like this. So whether it completes the circle or not, you should imagine the circle. Then you can answer questions properly. Okay. Had the magnetic field existed throughout space, it would have gone in that circle. But now it's only moving over a part of that circle before it leaves the magnetic field. That is what is going to happen. So is the idea clear to all of you? Are you able to understand why it happens like this? If you have any doubts, you can ask. The radius is still mv by qb itself, because it's the same force that it is experiencing, qvb. The speed is v, then the radius of curvature has to be mv by qb, but it's only a part of a circle, not a semicircle or a complete circle. Okay. Now let's get back to this. I'll erase these force vectors. So this is the center of the circle or center of the arc along which the particle moves. So path followed is an arc. As long as it is inside the magnetic field, it's an arc. Once it is outside, it will be straight line. Now you need to find out the time it spends inside the magnetic field. We know the speed with which it entered. The speed was v. And we know what the particle is doing inside the magnetic field. We should find out the time it spends, means the time it takes to go from here to here. Can any of you tell me an idea?
So can we use a relation like the time will be distance by speed?
Time is distance by speed, correct? We know the speed. How will you tell the distance, the length of that arc?
Like by finding the angle which it creates at the C.
Good. See, there is a general formula for length of an arc, if you all remember. L is equal to r theta. So let's visualize the angle subtended by the arc at the center of the arc. So this was the center. If you can tell this angle, you can tell the length of the arc. L is equal to r theta. We know the radius here already. R is equal to mv by qb. Okay. Can one of you think of an idea to derive this angle now? It's just geometry. The hint is in this. We know the angle at which it enters into the magnetic field. Okay. Using that, you have to tell the angle rotated by it. Okay. Think about it. I'll draw a better diagram to help you all understand. It enters at this point A with the velocity making an angle alpha with the x-axis. And it leaves from here, from this point B, with velocity like this. So any idea how to get that angle at C? As I said, it's simple geometry. The boundary now, which is the dotted blue line, is a chord to this circle. Right? Is a chord to the circle that it would have executed had the magnetic field been present everywhere. Fine. So if this angle is alpha, you can see on the lower side where it enters into the magnetic field. If this angle is alpha, alpha is with x-axis, the chord is in the y direction, then the angle inside will be 90 minus alpha. And from basic properties of circles, you can tell that this angle also will be 90 minus alpha itself. And if this is 90 minus alpha, then the angle outside is alpha. And if that is alpha, the angle at which the particle leaves the magnetic field is also alpha itself, because the boundary is a straight line. So it enters at an angle alpha, leaves at the same angle alpha. Fine. Now you imagine what effectively happened to the velocity. Velocity while entering into the magnetic field was this way. While leaving the magnetic field, it is this way. Right? This angle was 90 minus alpha. The other side, when it is leaving the magnetic field, that angle will also be 90 minus alpha. So can any of you tell me by what angle the velocity vector has rotated? You can see the initial velocity vector. You can see the final velocity vector. It would have gradually rotated from this orientation to that orientation. How much did the velocity vector rotate? Like Imagine them with their tails at a common point. How much is this rotation? Is my question. Well, that's very simple. Just look at the diagram and tell me. Answer will be in terms of alpha. How much is this angle?
Sir, is the answer 180 minus 2 alpha?
That's all. This angle on the right side, it is 90 degree minus alpha. So when the particle entered into the magnetic field, its velocity was making 90 minus alpha with the y-axis on the right side. When it is leaving the magnetic field, its velocity is making 90 minus alpha with the y-axis on the left side. So 90 minus alpha, another 90 minus alpha, velocity rotates by 180 degrees minus 2 alpha. That's the angle rotated by the velocity vector. Okay. Now, velocity is always tangential to the circle, and the position vector is always in the radial direction. The position vector, when the particle enters into the magnetic field, will be perpendicular to the initial velocity, and the position vector, when the particle leaves the magnetic field, will be perpendicular to that final velocity. So basically, the position vector has to rotate along with the velocity vector. So it's somewhat like this. You can visualize. Let's say this fluorescent pen, or the yellow one, is the position vector from the center of the circle, and this black one is its velocity vector. Now, as the velocity vector rotates, the position vector rotates along with it. So whatever is the angle rotated by the velocity vector, same will be the angle rotated by the position vector. Okay, because they should always remain mutually perpendicular to each other. They rotate together like this. Okay. Now we know the angle rotated by the velocity vector, 180 minus 2 alpha. Then the angle rotated by the position vector should also be 180 minus 2 alpha. That is the angle subtended at the center of the circle. By what? By the arc along which the particle moves. Okay. Now you can use L is equal to r theta. Let's go back to that diagram. The length of this arc will be L is equal to r. R is mv by qb, or just write the formula first. L is equal to r theta. So r is mv by qb. Theta is 180 minus 2 alpha, but 180 is in degrees. Now I hope you all are aware L is equal to r theta is applicable only when theta is in radians. You should never substitute the angle in degrees in this formula. Okay, so we write it as pi minus 2 alpha. Alpha should also be in radians itself. Okay, so that's the length of the arc. That is the distance that it travels inside the magnetic field. Divided by speed, you can find out the time spent inside the magnetic field. Okay. See, it may seem complicated at first, but all you need to do is visualize the angle by which it rotates. In fact, there's another way also. You need to find out the time spent inside the magnetic field. I got one idea that time is distance by speed. We made use of that. There is another way also to calculate time using angular velocity. We know angular velocity by definition is angle rotated by time taken. So you can say time taken or time spent inside the magnetic field is the angle rotated divided by the angular velocity. Angle rotated you will anyway have to find out, pi minus 2 alpha divided by angular velocity. We had discussed that in the last class. We know r is mv by qb. So omega, which is v by r, becomes qb by m. That's the angular velocity with which the particle rotates inside the magnetic field. You can use that. Divided by qb by m. The answer will be same whichever way you solve. Qb. That's the time the particle spends inside the magnetic field. Okay. Next, angular deviation. Angular deviation we have already calculated, pi minus 2 alpha. Okay, you'll need that anyway to find out the time spent inside the magnetic field. So questions based on this concept, they involve a little bit of mathematics, general concepts of circular motion, angular velocity, L is equal to r theta. You should be comfortable with all these, then you can easily answer questions based on this concept. Now I'll ask you another question. Same situation. Find out the maximum distance the particle goes into the magnetic field. Derive an expression for this. I'll show it to you in the other diagram. Just for convenience, if you want, you can call this angle as theta itself. Theta is known to us. Okay, so keep it as theta. Based on that, I want you all to calculate the maximum distance it goes into the magnetic field. So this distance is what you need to find out. Okay, instead of using 180 minus 2 alpha or pi minus 2 alpha, keep the angle as theta itself. Based on that, you answer. Again, this is a geometry question actually. The physics part is done. Any idea, anyone, to calculate that distance? Okay. I got one answer as r minus r cos theta by 2. So r into 1 minus cos theta by 2. I think that is correct. So as I said, it's just geometry. Just a moment. Center is C. Call this point as D. What is the distance from C to D? Complete distance.
The radius.
Radius. CD is the radius, which is mv by qb, and we know that. mv by qb. Let's keep it as r itself for now. So radius is known to us. And from that distance to get small d, like imagine that line CD. It so happens that CD is perpendicular to that chord. So there is a right angle triangle forming here, which you can take advantage of. Okay. In this right angle triangle, if you can calculate the base, subtract the base from the radius, you'll get small d. That is how we are going to solve. So let us remove this lower part. The total angle at the center was theta. then this half angle will be theta by 2. In this right angle triangle, we know the hypotenuse is r, which can be calculated. And we need this adjacent side now. Let's call it as x. So cos theta by 2, or you can directly tell x is equal to r cos theta by 2. That's all. C to D is r. From that, if you remove x, you will get D. Okay, so small d is equal to C capital D minus x. That becomes r minus r cos theta by 2. And r is mv by qb. You can substitute. Theta is pi minus 2 alpha. You can substitute. Okay. Fine. So if you substitute r as mv by qb, multiply it with 1 minus cos theta by 2, you see that b is in the denominator. Fine. So tell me now, if the magnetic field is stronger, will the charge go a greater distance into the magnetic field? That means will small d increase or will small d decrease? If the magnetic field is made stronger, nothing else is changed.
Decrease.
As you can see in the result, we find magnetic field in the denominator, right? So if magnetic field increases, the distance d is going to decrease. What that means is, see, the angle at which it enters is alpha, the angle at which it leaves is alpha. Magnetic field has nothing to do with that angle. What would change if the magnetic field becomes stronger is the radius. If magnetic field becomes stronger, the force will be more. It will take a sharper turn. So if you make the field stronger, it enters at this same angle, but it will leave quickly. Maybe like this. So the distance it goes into the magnetic field will be much smaller, will decrease. So they can ask you questions based on that also. In fact, they have already been asked in exams. They give you a situation like this and say there is a wall here. Okay. What should be the minimum strength of the magnetic field such that the particle does not strike the wall? Because if the field has sufficient strength, it can turn the particle before it touches that boundary, that second boundary. Okay, so questions based on that are quite common. I'll send you such questions in the worksheet. This concept is very important. You should be able to find out anything in such cases. Okay, angular deviation, how much time it spends. They can give you, like in this case, we assume there is magnetic field everywhere on the right side of the boundary. They can even give you situations like this. Charge is moving this way, enters into a magnetic field, and the magnetic field extends only up to a limited distance. Then what will happen? Here it will follow a curved path and it can leave from here. Such questions also you should be able to answer. And such questions you'll find in the worksheet along with hints. You'll be able to do it. But make sure you spend some time on this concept and get a perfect grip on it. You need to make use of some properties of circles, chords, and then the physics that you learned here. Radius is mv by qb, time period, angular velocity, such things. Okay, so this is what happens when a charge enters a magnetic field or when a charge moves in a magnetic field perpendicular to the field. Okay, we discussed a little bit of that in the last class and a little bit of it in this class. So two cases of motion of charge in a magnetic field are done. First case was velocity being parallel to magnetic field or velocity being exactly opposite to magnetic field. In that case, V cross B becomes 0. The charge does not experience any magnetic force at all. Second case was velocity being perpendicular to the magnetic field. In this case, if the field is uniform, it tends to execute circular motion as long as it is inside the magnetic field. Okay, now the third case. What if velocity is not along the same line as magnetic field, And it's not perpendicular also, it makes some other angle. So velocity makes a random angle theta with the magnetic field. Okay. For us to be able to visualize this properly, we need to take magnetic field and velocity in the same plane. So we can't take magnetic field in the z direction here, because then you won't be able to visualize the angle between velocity and magnetic field clearly. So let's say the magnetic field is this way, to the right. We are dealing with a uniform magnetic field itself. And you all know that for a uniform field, the field lines will be parallel with equal spacing between them. So let this be the magnetic field. Okay. Assume this is the charged particle and its velocity is in some random direction like this, making an angle theta with the magnetic field, uniform magnetic field. Right. Now we need to talk about what happens to this particle. Let's assume it's positively charged for now. If it's negatively charged, the force will act in the opposite direction. Now we know the force exerted by the magnetic field is Q V cross B. The cross product of two vectors depends on the perpendicular component of one vector. The component of one vector perpendicular to another vector. Like you all must have studied something like this. A cross B, or the magnitude of A cross B, is A multiplied with B perpendicular. You can also write it as B vector as it is multiplied with component of A perpendicular to B. Okay, that is how it becomes AB sin theta. Okay. So in this case also, the force acting on the charge depends on the component of velocity perpendicular to the magnetic field. You can look at it the other way also. You can keep velocity as it is and take component of magnetic field perpendicular to velocity. But our aim now is to describe the motion of the particle. To describe motion of any particle, not just this one, you need to look at the velocity vector. Okay, so we'll resolve velocity into two components by keeping the field as it is. So you can take one component of velocity parallel to magnetic field. That will be V cos theta. And you can take another component of velocity perpendicular to the magnetic field, and that will be V perpendicular, which is V sin theta. Okay. Now in this case, the magnetic field is in the x direction. And we had discussed in the last class, a charge executing circular motion in a magnetic field moves along that circle in a plane perpendicular to the magnetic field. Now here also you look, the velocity now is the sum of these two components. So if you write the force, it is Q V cross B, which is Q. V is now the sum of vector sum of V parallel and V perpendicular cross B. You can split this into two terms, Q V parallel cross B plus Q V perpendicular cross B. V parallel cross B becomes 0 because V parallel and B are in the same direction. Their cross product becomes 0. So the net force acting on the charge due to the magnetic field is only this much. And its direction will be in the direction of V perpendicular cross B. Okay. Now here in this diagram, if you see, V perpendicular is in the Y direction, B is in the X direction. Now Y cross X, if you do, the force will be in the Z direction into the screen. That's actually minus Z. Okay. So force is into the screen. Now, if you visualize it this way, assume this, okay, let's say this black pen is the velocity vector. Okay, it's pointed upward, but force is acting into the screen. So it's acting backwards like this. Due to that, what will happen? The velocity vector rotates this way, backwards, away from you. Okay, it continues to rotate and it executes a circular motion in this plane. Fine. Which way was the magnetic field? Magnetic field was to the right. Velocity initially, at the moment we have taken, the velocity is in the y direction, magnetic field is in the x direction, but force is in the z direction. So it executes circular motion this way. Which plane is this? Magnetic field is in the x direction, circular motion will be in the yz plane. Okay, so as a result of the magnetic force acting on it, this charged particle that is there moves in a circle in the yz plane like this. Okay, you need to assume magnetic field exists there also. Just a moment. Yeah. So it moves in a circle in the yz plane due to v perpendicular, but there is v parallel also. V parallel is velocity in the x direction. So as it tries to execute circular motion in the yz plane, it gets dragged in the x direction due to that v parallel component. So effectively what happens, this particle let's assume it was here. So due to v perpendicular, it tends to execute circular motion in the yz plane. Due to v parallel, it moves in the x direction. So executing circular motion in the yz plane and moving in the x direction, effectively it ends up following a helical path. So it's like a spring. When you see from one side, it looks like a circle. And so on. Fine. So when you look at it from this side, looks like a circle. Okay. And what is that circle's radius? We know r is mv by qb, but now the particle is executing circular motion only due to one component of velocity, not the complete velocity. It's only v perpendicular which results in that circular motion. So the radius of this helix, can any of you tell me how much that will be? It is executing circular motion due to v perpendicular or due to v sine theta. Then what will the formula for the radius be?
mv sin theta by qb.
That's all. mv perpendicular divided by qb. That is mv sine theta divided by qb. That's the radius of that helical path or the spring-like path that it takes. Okay. And this v parallel that is there, it makes it go forward along the magnetic field. Now the v parallel will not be affected at all by the magnetic field because v parallel cross b becomes 0. So this v parallel remains constant. And if v parallel is constant, every time it completes one circle, it will move by the same distance in the forward direction. Okay. What I mean to say is this distance will be equal to this distance, will be equal to the next distance and so on. What do we call this distance? We call it as pitch of the helix. So it executes helical motion with a uniform pitch. Pitch is basically the distance moved forward by the time it completes one revolution. You can imagine one revolution also. Let's say it starts from here, A. Okay. This whole thing going up, then coming down on the other side, back to the same point. Not same point, sorry, same level. That is one circle. When you see from the left side, it would have completed one circle. By that time, it would have moved forward by some distance. So it moves forward from A to B. That distance is what we call as pitch. Okay. And you can calculate pitch this way. Pitch is basically distance moved in the x direction. So that is velocity in the x direction multiplied with time. Velocity in x direction is v parallel. Time is the time taken to complete one circle. That's the time period of revolution. So this becomes v sine theta. Oh, no, v parallel is v cos theta. Sorry. So v cos theta multiplied with time period we know is 2 pi m by qb. So that gives the pitch of the helix. Okay. So to calculate pitch, we are making use of the fact that the velocity in that direction remains constant. If velocity is constant, speed is constant, pitch is a distance. So to calculate distance from constant speed, we use distance is speed into time. Time taken to go from A to B is the time taken to complete one revolution in the YZ plane. That is nothing but time period of revolution 2 pi m by qb. In that time, the horizontal, not horizontal, in that time, the displacement in the x direction is what we call pitch. Okay. So hope the formulas are clear. This is all you need to know about this case when velocity makes a random angle. It follows a helical path. That helix will have a uniform pitch. If no other forces are acting, it will be uniform. We will discuss some cases where there is an electric field applied this way. Then electric field, what it will do, it will accelerate the charge. So V parallel will change. And if V parallel changes, it will move by different distances in equal amount of time. Then that will become a non-uniform helix. Anyway, such cases we'll discuss in the next class. For now, if the magnetic field is uniform, it will move in a uniform helical path. Any doubts in this? Okay, let's quickly go through what all we discussed in today's class. So first we solved some problems based on ratio of radius, ratio of time period. Then we discussed, then some more problems based on the circular motion executed by a charge in a uniform magnetic field when its velocity is perpendicular to the field. These cases are very important. And then finally, we talked about what happens when velocity is not along the line of magnetic field and not even perpendicular to the magnetic field. Okay. So then you'll have to resolve velocity into two components, one parallel to it, one perpendicular to it. Parallel component will simply take it along the magnetic field. Perpendicular component will make it go in a circle. Now both will happen simultaneously. Effectively, it moves in a helical path. Okay. You can calculate the radius of the helix and the pitch of the helix. Okay, fine. Thank you all. We'll close this session here. I'll send you a worksheet. Make sure you solve as many problems as possible on this concept.